Hey guys, it's Miss Johnson, and I'm here to bring you our notes video for Unit 8 Notes 4, which is on rationalizing the denominator. So that is our learning target for today. We are going to learn how to rationalize the denominator of fractions. So here's the thing. We've talked about these already. These are the things that we're not allowed to have in a simplified form of a radical expression. We cannot have perfect squares under the radical. We cannot, and that's what we've been practicing working on, simplifying the radical and taking out those pairs of numbers, so perfect squares. We cannot have fractions underneath the radical, and we cannot have radicals in the denominator of a fraction. We're not allowed to have those three things. So the two that we're going to work on a lot today are the bottom two, these two right here. So we're really working on the fraction part of it and what happens when we have that. So the quotient property tells us, quotient property of radicals tells us that the square root of a over b is really just the square root of a divided by the square root of b. I can split those two apart, leaving them both underneath the radical sign. And we're going to use that to our advantage. Let's just take a look at number 1 and see if we can simplify this. So the square root of 15 over 12 is the same thing. If I reduce it, that is the same thing as the square root of 5 over 4. All I did there was take out the common factor of 3. And when I took out the common factor of 3, that gave me the square root of 5 over 4. Well, that's the same thing also as the square root of 5 divided by the square root of 4. That's what that quotient property tells me. And then in the bottom, the square root of 4 is just 2. So then I have the square root of 5 all over 2, and that's my simplified radical expression. There's nothing else that I can do with the 5. The denominator doesn't have a radical. There's no fraction underneath the radical, so I've taken care of all of those things. Square root of 21 over 7 in number 2. Reduce the 21. Again, I can divide by 3 there, and if I divide by 3, I end up with the square root of 7 over 9, which is just the same thing as the square root of 7 divided by the square root of 9. And we know that that square root of 9 is 3. So that's the square root of 7 divided by 3. Notice, by the way, that when I went from the square root of 4 to 2, there's no more radical sign on the bottom. Same thing here, square root of 9 to 3. No more radical sign over that 3 because I'm actually taking the square root, which makes that go away. So I'm left with the square root of 7 divided by the square, but divided by 3, which is simplified and covers all of my bases as far as simplified radicals. Now, what happens when we're left with a radical sign that's not a perfect square? 4 is a perfect square, we could take care of that. 9 is a perfect square, we could take care of that. But what about numbers that aren't perfect squares? And that's where rationalizing the denominator comes in. So just a reminder, a rational number is any sort of fraction. It's any sort of number that's written as some number in the numerator, some number in the denominator, and remember that that fraction bar in the middle means division. So when we have a radical left in the denominator, we have to rationalize the denominator. Okay, we can't leave it as the square root of an irrational number. So I am going to do these three things. I'm going to simplify the radical expression as much as I can before I take care of the denominator. Then I need to multiply the top and bottom by the radical that's left on the bottom. And we're going to see what that looks like. And then you have to go back and simplify again. So it's kind of a couple of steps here in our process. So don't forget that you can pause the video at any time if you need to take a minute to write down those steps. So let's move on to number 3. In number 3, I have the square root of 1/3. So here's what this looks like. This looks like the square root of 1 divided by the square root of 3. There's no way to simplify 1/3 any more than it already is. So I have the square root of 1 divided by the square root of 3. Now, 3 isn't a perfect square. It's not a perfect square. I can't do anything with it. It doesn't make any pairs. So I have to give myself another factor of 3. So what I'm going to do is I'm going to extend my radical here, and I'm going to give myself another factor of 3 in the bottom. But we all know if I multiply the bottom of the fraction by something, in order to keep it balanced, I also have to multiply the top by that same number. Okay, so I've added another factor of 3 into this equation or into this expression, and now the reason that's nice and works out for me is because now I have the square root of 3 over the square root of 9, and the square root of 9 is just a perfect square. It's the square root of 3 divided by 3 outside the radical. So this pair of 3's came outside to make that 1, 3 on the bottom. Okay, so I had to give myself a pair of 3's, or in other words, a perfect square, so that I had a number outside of the radical on the bottom. Now, a lot of people look at that fraction and see this 3 over 3, and they say, oh, that can be reduced. Well, not really. This number on the top is actually the square root of 3, not 3. So this one's not under a radical, this one is under a radical. I cannot reduce it any more than it already is. So I'm going to leave it as that, and it's simplified. Let's try number 4. So in number 4, I have the square root of 12 over the square root of 10. Or I'm sorry, the square root of 12 over 10. So remember that that's just the same thing as the square root of 12 divided by the square root of 10. I can also reduce those. 12 and 10 both have a common factor of 5. So if I reduce those, I end up with the square root of 6 divided by the square root of 5. Now, I can't do anything else with 6/5. There's no other way that I can reduce that. And there aren't any perfect squares in either one of these that I can take out. And I have this radical in the bottom. Not allowed to keep it like that. So what I need is, with the square root of 6 divided by the square root of 5, I need to extend my radical, and I need another factor of 5. But again, since I have another factor of 5 on the bottom, I'm going to have a factor of 5 on the top. So basically, I'm multiplying by the square root of 5 over square root of 5. Because now, this pair of 5's comes out front and is just a 5 without the radical. And that makes that radical sign disappear. And then on the top, I've got the square root of 30. And again, even though 30 and 5 have common factors, I can't reduce those because this one's under the radical on the top, but on the bottom it's not. So that is my simplified expression. Once the radical sign is out of the denominator, see, no more radical, no more radical. Once your radical sign is out of the denominator, then you're good. So we just have to create pairs so that we can take them out of the radical. Okay, let's try number 5. So in number 5, I have the square root of 10 over 3. I can't reduce 10/3 at all. There's nothing I can do with that. So I'm just going to call this the square root of 10 divided by the square root of 3, and I'm going to give myself another factor of 3 on the bottom, but when I do that, I give myself another factor of 3 on the top. So that gives me the square root of 30 divided by the square root of 9, and we know that the square root of 9 is just 3. So it's the square root of 30 divided by 3, and nothing else that I can do with that. Okay. Let's talk about the square root of 6 over 9. Now the square root of 6 over 9 is the same thing as the square root of 6 divided by the square root of 9. And the nice thing here is 9's already a perfect square. So just make it the square root of 6 divided by 3, because 9 is 3 times 3, and that pair would come out front. So square root of 6 over 3, and there we are. Let's flip over to the back and try some other ones. Square root of 27 over 15. So I need to split them apart. Actually, let's reduce them. 27 over 15 is going to give me the square root of, I can take out a 3. So the square root of 9 over 5. Okay, so I have the square root of 9 divided by the square root of 5. Can't do anything with the 5. The 9 I can. Now that's great. That gives me, because the square root of 9 is just 3, so that gives me 3 over the square root of 5. But here's the deal. I still have a radical in the bottom. Even though I simplified the top, that didn't help me on the bottom, so I've still got to fix that. I'm going to give myself another factor of radical 5, and I need a factor of radical 5 on the top. So square root of 5 is going to go up there. I end up with 3 radical 5 over 5. There's nothing else that I can do with that fraction, so that is my final answer. Let's take a look at number 8. In number 8, I have the square root of 5 over 12. So I can split that into the square root of 5 divided by the square root of 12. Okay. Now, that 12 on the bottom actually has some radicals that I can take out of there. There's a couple ways you could think of this. I can split 12 into 3 times 4. And I can pull this 4, because it's a group of two 2's, I can pull that out front. And now let's see what that does to my whole expression. I still have that square root of 5 on the top. I haven't touched it. On the bottom, I have the 2 out front with the square root of 3 left over. Okay, so that helped me a little bit, but all it really did was just leave me with a smaller radical that I still had to take care of. So either way, if you would have multiplied by a 12 up here and then simplified after, you're going to end up with the same result as if you simplified before, multiplied by the 3, and then gone from there. So I have the square root of 15 on top, and then on the bottom, this pair of 3's comes out front and gets multiplied by the 2. 2 times 3 gives me 6. So I have the square root of 15 over 6. Nothing else I can do there. Let's try number 9. In number 9, I have the square root of 3 over 21. And again, if we want to reduce this first, we can. So we could call this the square root of 1/7. All I did was divide by 3 there. Okay, so now I've got the square root of 1 on top, square root of 7 on the bottom, and I need to have another factor of 7. So I'm going to add another factor of the square root of 7, just extending that radical, putting a 7 underneath with it. So I've got the square root of 7 on top with the square root of 49 on the bottom. And again, that pair of 7's comes out, or in other words, if you think of the square root of 49, either way, you've got the square root of 7 over 7 outside. And don't forget, if it's under the radical and this one's not, you can't reduce them. They're not the same thing. Number 10, we're getting down there to the end. So square root of 4 over 10, that's the same thing as the square root of 2 over 5. So I have the square root of 2 divided by the square root of 5, and I can't leave that radical in the bottom. So I need another factor of the square root of 5, another factor of the square root of 5 on top as well. This comes out front. That's the square root of 10 over 5. Okay. Two more, number 11. Now I've got some variables thrown in there. That's fun. So let's think about what would happen here. Now there's no way to reduce this fraction, so I have to just leave it as it is. So that's the square root of 3 on the top, square root of 8x to the third on the bottom. Now, let's go ahead and reduce that 8x to the third. This is the same thing as 2 times 4, which is 2, and then 2 and 2, and then the 3x's. So this comes out front, that comes out front. So I have 2x, and then underneath I have a 2 and an x. And that was the bottom of my fraction. The top of my fraction is still that square root of 3. So, okay, that's a little bit nicer to look at. Now I still need to rationalize this radical part. I'm not worried about this 2x that's already out here. That's already outside of the radical, so I don't need another factor of 2x. I do need another factor of 2x for what's left underneath. So I'm going to multiply by a 2 and an x, and that means up here I'm also going to multiply by a 2 and an x. Oops, not 26, a 2x underneath the radical. So now the pair of 2's comes out, the pair of x's come out, and on the top, let's see what we have. We have 3 times 2, which is 6, so 6x. And then I had the 2x that was already there. I get another 2 from this pair, and I get another x from that pair. And putting that all back together, holy cow, 6x, 2 times 2 is 4, x times x is x squared. So the square root of 6x over 4x squared. And again, top is radical, bottom is not, can't reduce it at all. One more of these type with the variables. Again, I've got the square root of 7 over 18x to the 5th, and I cannot reduce that at all. 7 and 18 don't have any common factors, so I've just got to leave it as it is. So I've got the square root of 7 on top, square root of 18x to the 5th on the bottom. Let's take care of that 18x to the 5th. So this is the same thing as 2 times 9, which is 3 and 3, and then 5x's. And let's think of the groups that'll come outside. The 3's come, this pair of x's, that pair of x's. So I have the square root of 7 on top that I haven't touched yet. On the bottom, I pulled out a 3, an x, and an x. I'm left with the 2 and the x underneath. Now I've got to rationalize. So I'm going to extend this radical. And again, I'm not worried about the stuff that's already outside. As long as it's outside of the radical, it's fine. I am worried about this stuff that's underneath. So I need an extra 2x, which means I need an extra 2x on the top as well. So now the new top looks like the square root of 14x. On the new bottom, I'm going to have the 3, the x that were already there. Then I get a 2 from that pair, and I get another x from that pair. Let's put it all back together. Square root of 14x over 6x to the third. Whew. Okay. We have one application question to look at the bottom. It says the period of a pendulum is the time required for it to make one complete swing back and forth. The formula for the period P of the pendulum is P equals 2 pi times the square root of L over 32, where L is the length of the pendulum in feet. If a pendulum in a clock tower is 6 feet long, find the period of the pendulum. Okay, so I know that this is my L, which means I'm going to plug it in right there. So I have P is equal to 2 pi and then the square root of 6 over 32. All right. So now I need to reduce this. Let's simplify this and see what's happening here. So I've got P is equal to 2 pi. 6 and 32 have a common factor of 2. So I guess I could make that the square root of 3 over 16. Okay, getting better. Then I have 2 pi square root of 3 times the square root of 3 over the square root of 16, okay? And nice thing here, square root of 16 is just 4. So this is the same thing as 2 pi times the square root of 3 over 4. And if I put all of that stuff together, this is kind of like a fraction over 1. So when I multiply fractions, we go straight across the top and the bottom. So that's 2 pi times the square root of 3 all over 4. And then one last teeny tiny thing that I can do, reduce. 2/4 have common factors, and these are both outside of the radical, so I can reduce them. This reduces down to a 1, that reduces down to the 2. So I'm looking at pi times the square root of 3 over 2. That is the period of the pendulum in time, whatever that is. It must be seconds, I'm guessing. So the square root of 3 over 2. Now, if we think about that in terms of actual real time, if you walked down the street and said to somebody, what's the square root of, or pi times the square root of 3 over 2 seconds? That doesn't really make a whole lot of sense. So what we want to do is we want to find an approximation of this. So go ahead and plug that into your calculator. You've got 2 times the square root of 3. I'm sorry, pi times the square root of 3. So pi times the square root of 3, whatever that is, and then divide that by 2, and that is 2.7 is approximately what I get there. 2.72, and we'll call it seconds, because I think that's what they're referring to here. So, okay, that's going to conclude our notes video for today. So thanks for watching. Don't forget to hop back to Schoology and take that quiz, and I will see you all tomorrow.